In this video, I'm going to be doing a full breakdown of a difficult combination circuit problem that has series and parallel circuits within it, and then we're going to find the current flowing through each one of the resistors as well as the voltage drop. Now we're going to start with our first picture right over here in the top left-hand corner. We have a 20-volt source, and then we also have 5 different resistors. They're each color-coded, so we can kind of follow along as I redrew the circuit 3 different times. Now that's exactly what you want to do. So when you're taking a look at these compound or combination circuits that have a mix of series and parallel circuits within them, what you want to do is redraw them, simplify the look of them, and that really makes it seem much less overwhelming and much more doable to solve for all these different components. With that being said, let's go ahead and take a look at this. We have the electrons coming out, and they all have to go through the 5 ohm resistor. Now from there, they have a choice. They can either just go through the 10 ohm resistor and then all the way back. Okay, and then that path is right over here. It goes through the 5 and then goes through the 10. And then after they reach this junction, if they don't go through the 10, they have 2 possible paths. So I'm going to take a look at both of those possible paths and see what happens. If I take this path, it's going to go through the 20, and then it would also have to go through the 15 as well before returning back to the voltage source. So then that means that I have a branch of a parallel circuit where it must go through the 20 and 15. Now, also, there is another path right here where it has to go through the 5 and then also through the 15 as well, and then again all the way back to the low potential end of our 20 volt source. So we have another path where it's going to go through the 5 and then through the 15. So now that you see this redrawn on the bottom, we have a junction over here where it splits and either goes through just the 20 or the 5, but both of those must go through the 15. So I made a mini parallel circuit over here where it either goes through the 20 and then the 5, and then both of them must go through the 15 to return back to the 20 volt source once again. Now this over here is definitely way easier to comprehend than this top one over here with some angled wires. Now from there, we're going to collapse it 2 more times. And the way we're going to do that is we're going to take our 20 and 5 ohm mini parallel circuit and then work that down into a single resistor. So how we're going to do that is we just add up the inverse of each of them, 1 over 20 plus 1 over 5, and that's set that equal to 1 over RT. And when you do that, you basically get 20 over 5, which is 4 ohms. And then eventually we collapse the 20 and 5 down to a single 4 ohm resistor. So the orange and blue one got combined into this 4 ohm resistor, which you can see with the orange and blue included in the picture. Next, we're going to collapse it 1 more time. Now we have a mini series circuit here with the 4 and the 15 together, and those 2 together are going to act like a 19 ohm resistor because everything that goes through this branch will have to go through the 4 and the 15, so it's going to act like a 19. So we're going to do 1 more calculation where we have a 10 ohm resistor in the top branch and then 19 ohms total in the bottom, and that equals 1 over RT. Now, what I typically do there is I sum these 2 numbers up in the calculator because they aren't easy fractions to add, and then just cross multiply that number with that RT. And then my RT came out to 6.55 ohms. So then this entire parallel chunk over here got collapsed down to 6.55, which includes the purple, orange, blue, and green resistor. Now the final look of my collapsed circuit is now very simple. It's just a 5 ohm resistor and a 6.55 ohm resistor all collapsed down into one single series circuit. So if I go ahead and add those 2 together, we know that the total resistance for those two combined is just the sum, which is just 11.55 ohms. And with that, we can also find the current. So we can also just go ahead and take our 20 volts and divide it by the resistance using Ohm's law. And then we have a current of 1.73 amps as our total current. Now with any series circuit, everything in the circuit receives the same amount of current. So both of these experience 1.73 amps flowing through them. And if we wanted to find the voltage drops, all we have to do is I times R, which is our gray current times our individual resistors. So then this one would end up dropping 8.65 volts, and then this one over here would be 11.33. And then because these are some rounded values, everything's not going to be end up being perfect when you combine them because they're all approximations. So if I add these two up, they're a little bit short of that 20 volts because of some rounding. Now let's go ahead and work our way backwards a bit. So we have everything for our final completely collapsed circuit. And then now when we go back to this one over here, we know a couple things about it. We know that each of these parallel branches gets 11.33 volts. So with that being said, anytime you have two out of the three variables for Ohm's law out of V, I, and R, you can always get the third. So if we know the voltage is 11.33 for each branch, then V over R equals I. So that means the current up here is 1.13 amps. Now going down to the bottom part, it does get a total voltage of 11.33. So if you take 11.33 volts divided by the total resistance of the branch, which is 19, then you get the current. The current for that whole bottom portion is 0.6 amps. So we have 0.6 amps flowing through each one of those because they're in series together. Now again, we have two out of our three variables, so you can do I times R, 0.6 times 4 and 0.6 times 15, and then we can get our voltage drops for each one of those, and then that would come out to 2.4 volts being dropped through the 4, and then that would come out to 9 volts. Now we're going to slide back one more step again, and we have everything figured out for the 10 ohm resistor right over here, so I'm not going to have those filled in. But, well, actually, let me just go ahead and write them in anyways. 1.13 amps, and then 11.33 volts. So now when we're going to these parts over here, we have everything covered for our 15 because we did that one earlier. So this one experiences 0.6 amps of current and a voltage drop of 9 volts. So this 4 ohm resistor, remember, is a combination of the orange and blue as shown by the colors there, had a 2.4 voltage drop. So each branch in a parallel circuit receives the same voltage drop. So this is 2.4 volts and this one is 2.4 volts. And again, we have two out of our three variables, so we can do V over R to get our I, and then the current for this one then is 0.12 amps, and then the current for this one over here is 0.48 amps, and then that 0.48 plus 0.12 does equal that 0.6 that flowed through that series circuit from the initial diagram. Now going to our 5 ohm resistor, we didn't fill that one out, but we did right over here. So I could just go ahead and transfer those numbers over and say this is the 8.65 voltage drop, and it gets the full 1.73 amps total. So that covers each one of our different resistors. We know how much current flows through each one and what the voltage drop is through each one of them. So the process of taking a fairly complex circuit and figuring out what the current and voltage drops are through each one of the different parts is definitely redrawing it and simplifying the look as much as possible, and then collapsing each parallel branch down until it simplifies as much as possible. From there, once you find some major components like we did over here with the current and some voltage drops, you work your way backwards and use some of your main concepts and rules, such as each parallel branch has the same voltage drop and that the current splits and sums up to the same total current once it reaches one wire again. And use those different ideas and basically just using Ohm's law a bunch, and then you can figure out all of the rest of the currents and voltage drops. So I hope that was helpful to you. Thank you for watching and listening.